Good morning, my dear students. Today we are going to discuss about the real numbers and their decimal expansion. As we know, we have two type of numbers, real numbers, rational and irrational. So we are going to differentiate rational and irrational numbers according to their decimal expansion. Just to explain this, we are going to consider some of the examples. Like we are taking some fractions 10 by 3, 7 by 8, 1 by 5 and 1 by 7. Now we are going to conclude by taking their decimal expansion. So very first we are taking 10 by 3. If we divide 10 by 3, 3 threes are 9, we will get the remainder as 1. Put the decimal, again take the 0, we will again divide it by 3, 3 threes are 9, we will get again remainder 1. So again 0, 3 threes are 9, again remainder 1. As you see, the process goes on up to infinity, and again we will get the same remainder as 1. And the expansion of 10 by 3 is 3.3333 and so on up to infinity. Now consider another expansion which we have 7 by 8. We have to divide 7 by 8. So take the decimal, as 7 is a smaller number than 8. That becomes 70. Now 8 8s are 64. So the remainder is 6, 60. 8 7s are 56. Remainder is 4, 0. 8 5s are 40. So here now I'll get the remainder as 0. So the decimal expansion of 7 by 8 is 0.875. Now consider the another, that is 1 divided by 5. So again put the decimal. Now 5 2s are 10. So the remainder is 0. So the decimal expansion of 1 by 5 is 0.2. Now if we will take the decimal expansion of 1 by 7. Decimal 10. 7 1s are 7. Remainder is 3. 7 4s are 28. Remainder is 2. 7 2s are 14. Remainder is 6. 7 8s are 56. Remainder is 4. 7 5s are 35. Remainder is 5. 7 7s are 49. Remainder is 1. Now if you check, we will get the remainder as 1. So the process again starts from that same, and we will get the same repetition of the digits again and again. So we have the decimal expansion of 1 by 7 is 1 4 2 8 5 7. Again 1 4 2 8 5 7 and so on. Now look at their decimal expansion. When you have what you have noticed in decimal expansion of 7 by 8 and 1 by 5, after a certain stage remainder becomes 0. But in the expansion of 10 by 3 and 1 by 7, remainder start repeating themselves. But when the remainder repeats, then we get a block of repeating digits. As in 10 by 3, we will get the same digit 3, 3, 3 and 3. So we can write it as 3.3 bar because 3 repeats again and again. And in the 1 by 7, we'll get the repetition of digits 1 4 2 8 5 7, again 1 4 2 8 5 7, again 1 4 2 8 5 7. Clear? So what we can conclude? So we can define the rational numbers is of the form p by q, where q is not equals to 0. And on dividing p by q, we get two results. Either remainder becomes 0 or never becomes zeros but block of repeating digits. So the rational numbers are either terminating or non-terminating but recurring. It means either their remainders become zeros, or if it is not 0, then it is recurring, means they are repeating. So how can we define an irrational number? So this is the definition of the rational numbers. We can easily define the rational numbers by checking their decimal expansion, that whether the decimal expansion is terminating. If it terminates, then it is a rational number. If it is non-terminating but repeating, then it is again a rational number. But how can we define the irrational numbers from the definition of a rational number? So we can define irrational numbers are those numbers whose decimal expansion are non-terminating and non-recurring. Means their decimal expansion never terminates and never repeats. It goes up to infinity, and the digits, block of digits, we do not have any block of digits which repeats again and again. So those type of numbers are called as irrational numbers. Now for example root 2, root 3, root 21, or we can take it as pi. Now the question arises, pi, we take the value of pi is 22 by 7. But 22 by 7 is a rational number as it defines the definition of rational number. It is of the form of p by q. See, pi is the irrational number, but pi is a irrational number, but we take pi value as 22 by 7, which is the approximate value, of pi, and that value is rational value. But pi is a irrational number because the decimal expansion of pi is 3.14159265387932384 and so on. It goes up to infinity. Now if we see root 2, the decimal expansion is 1.414213563095048801 and so on. If you see the decimal expansion, it is non-terminating and it is non-repeating also. If you see, we do not have any block of digits after which the same pattern repeats again and again. So these type of numbers are called as irrational numbers. Clear? And how can we write the irrational numbers? See, they are mainly the numbers which have square root numbers in which the number do not have and the number which is not a perfect square of any number. That square root number is called as the irrational number. Like root 2, all prime numbers, we can say all prime numbers, or the numbers which do not have any perfect, which are not the perfect square of any number, like root 21, root 2, root 3, root 5, root 7. Clear? So they all are irrational numbers, and mainly the pi we consider is at a irrational number, but we consider its value 22 by 7, which is the approximate value, and that value is a rational value. Let's start the exercise 1.3. So before that, we conclude our introduction that the real numbers are of two types, rational and irrational. Rational, which are terminating, if non-terminating, then repeating. Irrational, which are non-terminating and non-repeating. For example, 0.5, 3.796, 0.3 bar, 1 by 7, 1 by 17, etc. They all are rational numbers. Irrational, root 2, pi, root 15, 2.01. Yes, one more. How can we write the irrational numbers except root values? See, you can take any decimal expansion, but the condition is that decimal expansion should not be terminating and should not be repeating. For example, I can write it as 1.41, 411, 4111, 41111, 41111, and so on. See, the series is non-terminating because it goes on, and we do not have any same pattern of the digits which again repeats again and again. So this is an example of irrational number. Now let's start the exercise 1.3. Question number 1. The question number 1 we have, write the following in decimal form and say what kind of decimal expansion each has. So very first we have 36 by 100. So we can write it as 0.36. So its decimal expansion is 0.36. Next we have to find out the decimal expansion of 1 by 11. Divide 1 by 11. As 1 is a smaller number, put the decimal. 1 0, 1 more 0, 11 nines are 99. We will get the again remainder 1 0 0 0, nines are 99, again remainder 1. So it goes again and again. So the decimal expansion of 1 by 11 is 0.09 bar, because 0909 again we will get the 090909 and 09. So the decimal expansion of 1 by 11 is 0.09 bar. The third is the decimal expansion of 4 1 by 8. 4 already is there, so we have to find out the decimal expansion of 1 by 8. Put the decimal. 0, 8 ones are 8, 2 is the remainder, 0, 8 twos are 16, 4 is the remainder, 0, 8 fives are 40. So the here remainder is 0. So the decimal expansion of 4 1 by 8 is 4.125. Clear? Similarly, you can do the rest of the parts. 3 by 13, 2 by 11 and 329 by 400. Only you have to divide and check whether they are terminating. If non-terminating, then find out the block of pattern which repeats again and again. Question number 2. We have, as you know that 1 by 7, the decimal expansion is 0.142857 bar. Can you predict what the decimal expansions of 2 by 7, 3 by 7, 4 by 7, 5 by 7, 6 by 7 are without actually doing the long division? As it is given that, now see the solution. We have 1 by 7 is equals to 0.142857 bar. Clear? We have to find out the value of 2 by 7, 3 by 7, 4 by 7, 5 by 7 and 6 by 7 without actual doing the long division. How? See, 2 by 7 we can write it as 2 into 1 by 7. 3 by 7 we can write it as 3 into 1 by 7. 4 by 7 we can write it as 4 into 1 by 7. 5 by 7 we can write it as 5 into 1 by 7. 6 by 7 we can write it as 6 into 1 by 7. Now in all, put the value of 1 by 7 and multiply with the given numbers, like 4 into 2 into 0.142857 bar. So after multiplication we will get 0.285714 bar as the block of the numbers which repeats again and again remains the same. So put the bar on all the numbers. Only you have to multiply with the digits. Now 3 into 0.142857 bar. So it will give us 0.428571 bar. 4 into, it will give us 571428 bar. Similarly 5 and 6. When you multiply with the required value of 1 by 7, with the given value of 1 by 7, you will get your required result. It will give us 714285 bar and 0.857142 bar. Hence, we can find out the value of 2 by 7, 3 by 7, 4 by 7, 5 by 7 and 6 by 7 without doing the long division, only by the value of 1 by 7. Now, question number 3. We have express the following in the form of P by Q, where P and Q are integers and Q is not equals to 0. Means now the decimal expansion is given to us and we have to convert it into P by Q form. So very first we have 0.6 bar. Clear? So very first let x is equals to 0.6 bar. Let x is equals to 0.6 bar. Now remove the bar. So it means only we have bar on 6. It means 6 repeats again and again up to infinity. When you remove the bar, you have to write 6 again and again up to infinity. So it can be written as 0.666 and so on up to infinity. Let this is the equation number 1. Now check the number of digits which repeats again and again. Only the 6 is the number of digit which repeats again and again. So multiply that number of zeros to the given value of x. So we have only one number which repeats again and again. So we have to multiply by 10. Multiply equation 1 by 10 on both sides. So multiply 10 into x is equals to 10 into 0.6666 and so on. When you multiply, it will give you 10x. When you multiply this side, 1 0, we are multiplying with the 10, we have 1 0. So the decimal is going to be shifted to the 1 place. So shift the decimal, we will get 6.666 and so on. Consider it equation number 2. So what you have to do now, subtract equation 1 from equation 2. Subtract. So we have equation 2, 10x is equals to 6.666 and so on. And equation 1 is x is equals to 0.666 and so on. Now subtract both the equation. When you subtract 10 minus x, it will give you 9x is equals to 6 minus 0 gives you 6 point. 6 minus 6, 0, 6 minus 6, 0, 6 minus 6, 0 and so on. It means after decimal, all the digits becomes 0. Now what we will get? 9x is equals to 6 or x is equals to 6 by 9. Or we can write it as 2 by 3. So 0.6 bar can be written as 2 by 3. Clear? Similarly, look at the second part. We have 0.47 bar. Let x is equals to 0.47 bar. So we have bar on the 7. We can write it as 0.47777 and so on up to infinity. Let this is the equation number 1. So 7 is the only digit which repeats again and again. So we have to multiply by multiply by 10 to equation 1 on both sides. So what you will get, 10x is equals to 10 into 0.4777 and so on. So 10x is equals to, shift the decimal to the another one digit. So we will get 4.777 and so on. Let this is equation number 2. The same procedure, subtract. Equation 2 1 from equation 2. Now subtract it. We have 10x is equals to 4.777 and so on, and x is equals to 0.477 and so on. When you will subtract, 10 minus x, 9x is equals to 4 minus 0, 4, 0.7 minus 4, 3. And after this, all digits becomes 0 because we have 7 minus 7, 0, 7 minus 7, 0, and so on. All the same, we have same digits, 7, 7, 7, and so on. So now we have 9x is equals to 4.3, or we can write it as x is equals to 4.3 by 9, or we can write it as x is equals to 43 by 90. So 0.47 bar, only the bar is on 7, is equals to 43 by 90. Clear? Similarly, you can do the third part, that is 0.001. Here we have bar on the 3 digits, so we are going to multiply x by 1000. Clear? Now look at the question number 4. That is, we have express 0.9999 and so on in the form P by Q. Are you surprised by your answer? With your teacher and classmate, discuss why the answer makes sense. So again, very first we have to express it in the form of P by Q. So same, let x is equals to 0.9999 and so on. Clear? So next step is, we have, see how many number of digits are repeats again and again. Only the 9 is the number which repeats again and again. So it can be written as 0.9 bar. So let this is equation number 1. It means we have to multiply equation 1 with 10. Multiply equation 1 with 10 on both sides. On both sides. So what you will get, 10x is equals to 10 into 0.9999 and so on. Shift the decimal, one digit shift करेंगे. So we have 10x is equals to 9.999 and so on. Let this is equation number 2. Now the same, subtract equation 1 from equation 2. That is 10x is equals to 9.999 and so on. X is equals to 0.999 and so on. Subtract it. You will get 9x is equals to 9. After decimal, all digits becomes 0. So we can write it as 9 by 9, and which is equals to 1. So it means 0.99999 is equals to 1. Why? Because it's 0.99999 and so on. It's approximately equals to 1, or we can say it very, very, very close to 1. That is why its value is equals to 1. Now look at the question number 5. Next, we have, what can the maximum number of digits be in the repeating block of digits in the decimal expansion of 1 by 17? Perform the division to check your answer. Now I have already done the division. I can show you. See, when we divide 1 by 17, take the decimal. If you see the division, see how long the division is. And see, after the 16 number of steps, we will get the same remainder. And when we will get the same remainder, it means the process repeats again. So what is the decimal expansion? It becomes 0.08823529411764 So it means it repeats after 16 digits. So that is equals to bar of the 16 digits. So the decimal expansion of 1 by 17 is 0.0588235294117647 bar. It repeats after 16 digits. Now, question number 6. That is, look at several examples of the rational numbers in the form p by q, where q is not equals to 0. And p and q are integers with no common factors other than 1 and having terminating decimal representations. Can you guess what property q must satisfy? Just to explain this question, let's just take some examples. I'm taking some of the fractions, clear, in which p and q both are integers and they do not have any common factors other than 1. So let's just take, I'm taking 1 by 2, 1 by 4, 7 by 8, 30, 39 by 25. I can take 19 by 20, 31 by 16, 7 by 125. I'm taking some of the examples. They all have terminating expansions. You can check it. They all have terminating expansion. Now, if you check 1 by 2, 1 by 4, 7 by 8, 39 by 25, 19 by 20, 31 by 16, 7 by 125. It can be written as 2 into 1. It can be written as 2 into 2 into 1. It can be written as 7 by 2 into 2 into 2 into 1. And it can be written as 5 into 5 into 1. It can be written as 19, 2 into 2 into 5 into 1. That is 2 into 2 into 2 into 2 into 1. And this is 5 into 5 into 5. And which can be 2 in 1 by 2 raised to the power 1, 1 by 2 raised to the power 2, 7 by 2 raised to the power 3, 39 by 5 raised to the power 2, 19 by 2 raised to the power 2 into 5 raised to the power 1, 31 by 2 raised to the power 4, 7 by 5 raised to the power 3. Now what you can conclude from this? See, if you see here, the denominator is either 2 or powers of 2 or 5 or powers of 5, or we can say both, whether the power of 2 or the power of 5 or multiple of 5 and 2. So it means when p by q has terminating series, decimal expansion is terminating, when p by q has terminating decimal expansion, the q must be of either a 2 or power of 2 or a number 5 or the powers of 5 or the both. Like we have both. Again, when they have both 5 and 2 powers of 2 and 5, we have the decimal expansion as terminating. So the property which q must satisfy if the rational number has the terminating expansion, then the q must be 2 powers of 2, 5 powers of 5 or both. Thank you. Next, question number 7. Write 3 numbers whose decimal expansions are non-terminating, non-recurring. Non-terminating, non-recurring means the number must be a irrational number. It means we have to write down an irrational number. We have to write down 3 numbers, but we have to write down their decimal expansion. So consider any decimal expansion which is non-terminating and non-repeating. Like I'm taking 1.21, 211, 2111, 111, 21111, and so on. It is non-terminating, non-repeating. I can take another. I can take 01, 011, You can take 1 1, you can take 2 2, you can take 3 3. Only the method is we don't want any terminating series, and we don't want to show any recurring series. The pattern should not be same, and it is non-terminating. Then it is a irrational number. You can write it as any number, 1 1 1, and so on. Or we can write it as 1.21334790156742156001, and so on. They all are irrational numbers because they are non-terminating and non-recurring. Now the question number 8. Good question. Find different irrational numbers between the rational numbers 5 by 7 and 9 by 11. We are having two rational numbers, 5 by 7, 9 by 11. And what we have to find out? We have to find out three different irrational numbers between them. So very fast. Between any two rational numbers, there are infinite irrational numbers. If we have any two rational numbers, in between them we have infinite irrational numbers. Now how can we write down their irrational numbers? Very fast, write down their decimal expansion. Like we have done earlier in question number 2. The expansion of 5 by 7 is 0.714287. If you are not having, then find out. And 9 by 11, the decimal expansion is 0.81 bar. It means we want a number which is, we want irrational numbers which is greater than 0.71 but less than 0.81. So write down any number. I can take it as 0.72, 722, 722, 222, and so on. Only the question is it should not be terminating and non-repeating. I can write 27, 721, 7211, 72111, 72111, and so on. Or I can write it as 78, 788, 7888, 78888, and so on. So we can write infinite numbers in between 5 by 7 and 9 by 11. Hence, we have completed our exercise 1.3. No, we have one more question, sorry. Now let's just look at the question number 9, last question. That is, classify the following numbers as rational or irrational. Now we have to check which number is a rational or which number is not a rational number. As 23 is the prime number,